constraints, suggestions? Yes.
This or upload the video section for
they should be here. See the problem. Yes, will be uploaded soon. I'll ask Iskandar to do it again. Thank you. So that was a complaint. Any suggestions? That was a concern. Any other questions? We are in an off week in terms of exercises, so we will write here constraints, constraint derivatives, so we'll talk about joints today. Next week, Thursday, and this also has just been posted to do, we will have an exercise, and there's a bit of homework to do. This looks like a lot, 3 problems. I want to show you what we're actually doing in this homework. Number 1, you got a new class, or the 2 new classes that are called bound coordinate system and bound vector. This is not something that exists in physics because coordinate systems and vectors don't have an origin. Like we normally have to take them separately, point and the vector and the coordinate system. Here we're combining them into one object mostly for graphics purposes because we want to generate translational and rotational movement for coordinate systems shouldn't be drawn at the origin, and this is what these 2 classes do. There's a little bit of stuff that you have to go in to make this work, mostly to make sure you have a look at those 2 class files, but also to introduce you to this notion of the set routines that we have in MATLAB that I explained briefly in the last exercise. So this should be super quick. And then I will ask you to do or extend a file that is called rigid body kinematics. So this is a class that describes the kinematics of a rigid body, which basically means it's a collection of a position of a point, orientation of a body fixed coordinate system, and then for vectors, linear angular velocity, linear angular acceleration. That's basically what we need to describe a body, and this class basically has variables or basic properties as variables. Plus graphics. Now that is then a bit of a question how to make this look nice, but at the very basic core, we're drawing coordinate systems. What you will also have to implement is basically a version of 8C in our last exercise, where we said we integrate rotational motions. And here we call this integration step delta t, which is going to be a function of a method which within this class, rigid body dynamics class. And what it does is basically, from the outside, someone sets these properties. Right? Accelerations, angular accelerations. And there's also some values stored already for these, velocities and positions which orientation. And what integration step does is that it basically assumes that these values are constant over some period delta t and updates those and those. Simple Euler integration step that uses this idea of object-oriented programming, that it can look up what these quantities are, does some calculation on them, and then updates them in the object itself. There is some test cases here which also come with a additional function. Positions of a point on the body, velocity of a point on the body, and acceleration of a point on the body. This is straight up the implementation of so this is still kinematics. See how far I have to go back to show you this. These equations here. Position, velocity, accelerations. points of bodies, and we want to implement those as a function of this rigid gravity that I expressed. So once you define E and the orientation, you can get the position of any other point Q, and all of these functions, all they require is this vector RBQ in the coordinates. And then there's again some test cases. If you do this, about
half of you will see spirals, and about half of that half will claim they did everything wrong and I screwed this up. This is statistical data from past terms. And the reason why I say that is because I want to tell you no, this is the correct result. So if you see spirals, think again. And think again about the transport theorem. And think again when you integrate things, right, in this integration step, what do you integrate, right? You integrate coordinate numbers, but at the same time, velocities and accelerations are given as physical vectors. So there has to be some connection that involves potentially moving coordinate systems, right? So if you see spirals, that's my tip. Think about the transport theorem. Think about whether vectors are numerical. This is where you do the math, or physical. This is what is written here, right? That is a physical velocity. That's a physical acceleration, not the derivative of a numerical velocity. And then there was 16. 16 is a pen and paper question that goes into this idea of inertia matrices. And what I want you to do is to compute the inertia of certain objects, an ellipsoid, a cuboid, collection of 6 points, and so on. And then what we will do is we will invert these relationships and use them to visualize inertia, right? If I give you an inertia matrix, you can visualize this with an inertia ellipsoid, so an ellipsoidal body that has the same inertial properties, a rectangular body that has the same inertial properties, or 6 points. There may be a, this comes later, right? And all you have to do is to prepare this with pen and paper. In the exercise itself, we will try to simulate the motion of rigid bodies. And to do that, we will take advantage of everything that was done before. We will use the equations of motion, the Newton-Euler equations of motion that we derived in the last lecture. So these guys, to compute an angular acceleration, right, an omega dot, and then basically use the integration step that we do as the homework. This guy here, right? So we then basically set the omega dot and the a dot to these quantities here, and then use the integration step to generate a simulation. And with that, we then can simulate how rigid bodies behave in zero gravity if they're subject to no external torques. And you may have seen those results before, that there's a stable rotation axis, an unstable rotation axis, and so on. So that's the whole point of this exercise number 3. Questions? Then I want to start a new chapter, quite literally, chapter 3. And this now concludes the part that I consider to be a repetition, and you can kind of tell with the templates. Right? So we will be going a little bit slower now, trying to really create this content together. And I have a question for you. Is a joint, and maybe we do this show of hands, is a joint enabling motion or restricting motion? Who thinks a joint is enabling motion? Who of you thinks a joint is restricting motion? And then there's some people who never raised their hands. How come not?
Just wasn't sure. I mean, it's kind of difficult depending on how you define it.
I think that's the correct answer, right? It's a philosophical question, and it depends a lot on your point of view. And I think a prime example is skiing, right? You go skiing, you need your knee joint. If your knee joint is stiff, right, you cannot ski, or at least would be very, very uncomfortable. So your knee basically allows your leg to bend. So your knee joint allows motion. On the other end, right, your knee joint prevents your lower leg to fall off your upper leg. And that is one of the, well, this is one of these famous skiing injuries that you tore your ACL, your anterior cruciate ligament, your Kreuzband. Do you know how knee joints work? Sorry, it has nothing to do with mechanics. But the idea is basically you have this guy, that's your femur head, and then you have your tibia, so the bone in your lower leg. And how are they connected, right? How are they connected that this part doesn't fall off? There are muscles, but there's also a tendon, a ligament.
It was like a plate height, and that is connected with a crossbone.
That's the patella, but that is actually just connected to muscles up here and muscles down here, so it doesn't keep the knee joint together. So this is your Kniescheibe, patella. Sorry?
There's some kind of fluid between the...
There's fluid, which is true, right? Reduces friction, also doesn't keep the knee together. You never wondered why your knee doesn't fall off? I'm asking this because, right, for example, this would be your hip joint, right, where the socket and the ball, you cannot really get it out, right? There's a rigid connection. How is that connection then here?
There are slight ligaments and there are cross ligaments.
Yes, so there's one ligament going this way and another ligament going this way. And they're crossed, that's why they're called the crucial ligaments, the anterior crucial ligament, the posterior crucial ligaments, and they basically keep your knee from falling off. That's their function, right? And in this way, right, the knee joint restricts motion because your lower leg doesn't fall down. And if you have an ACL injury, that mechanism, right, is physically broken, and your knee joint doesn't work anymore. So, we have sort of a dual perspective on joints, and this is going to be sort of my first part here of this chapter. Joints are enabling and restricting motion at the same time. And this is a bit a question of perspective. And we will actually introduce two mathematical formalisms here that take into account both of these perspectives. But sort of the basic idea is that I have a multi-body dynamic system that consists of a number of bodies, and we call this number NB, the number of bodies. And those bodies have 6 times NB independent degrees of freedom in 3D, right? In the planar case, we have 3 times NB, so just 2 translations, 1 rotation. DOF's degrees of freedom. And without the joint, those would be independent. Those would be all the degrees of freedom that we get, but now they're restricted. And they're restricted by a number of constraints. Number of constraints is NC. And the ACL is one of these constraints, right? If you think about our door, there's a hinge. You can actually see it right in the corner. There's a hinge, and in that hinge is a pin. If I take the pin out, I can move the door freely with 6 degrees of freedom, 3 translations, 3 rotations. If I move it there, put the pin in, that pin restricts 5 of these degrees of freedom. I cannot move the door anymore, right? The 3 translations are blocked. I cannot turn it this way. I cannot turn it that way. All I can do is I can turn it this way, right? So that one little pin introduces 5 constraints and allows the door to move only in one way. More general, right? The constraints constrain the motion of these bodies to move in NQ ways. And NQ refers to the number of joints, or more precisely, motion primitives. Right? I say motion primitives because sometimes one joint can allow multiple degrees of rotation. So my hip joint, for example, has 3 motion primitives: abduction, adduction, flexion, extension, and then internal rotation and external rotation. Those are basically the 3 motion primitives of my hip joint. So one joint, 3 motion primitives would be described by 3 variables N, Q. So here's a little example how to set this up, right? So I have somewhere a wall, and I have a first body, and I have a second body. And originally, these bodies in 3D would have each 6 degrees of freedom. But then I go ahead and put in these pins, right? And each of these pins corresponds to one constraint. So this would be a constraint 1. This would be a constraint 2. And those are multidimensional constraints, right? In 3D, each pin would restrict 5 directions of motion. In 2D, each pin would restrict 2 directions of motion. And because of that, then my bodies, B1 and B2, cannot move independently anymore. And if I want to, I could describe the remaining motion simply through these motion primitives, in this case, the angles of the rotational joints. In terms of numbers, right here we have 2 bodies, which in 3D are giving me 12 independent degrees of freedom. I have 2 constraints, but each constraint is basically removing 5 degrees of freedom, right? I cannot move down, I cannot move over, I cannot move in this direction with a hinge here. So translation's fully blocked. I cannot rotate this way, I cannot rotate that way. Another 2 rotations blocked. So I take away 5 degrees of freedom per joint, and I am left with NQ equals 2. In 2D, similar story. NB is still 2. But in 2D, we would just have 2 translations and 1 rotation per body. So 6 degrees of freedom. How many constraints do we have in 2D per joint? 2, right? I cannot move in X direction, I cannot move in Y direction. So 2 times 2 equals 4. And in 2D, we would also have 2 remaining degrees of freedom, so 2 motion primitives. What's sort of the relation between these now? So if I'm trying to compute the number of motion primitives. Say that again? So NB, and now I have, of course, to say times number of degrees of freedom. So if I do this first for planar, I would get here times 3 minus number of constraints. So this would be in 2D. And in 3D, number of bodies times 6 minus the number of constraints. That is in 3D. Let's do a quick example. Sorry. And my example is a 4-bar linkage. And I actually brought a 4-bar linkage. This is a 4-bar linkage. And I will make the assumption that one of the 4 bars is rigidly bolted to the ground. And then I have a joint here, a joint here, a joint here, a joint here. And between these joints, I have the other 3 links. So 1 link connected to ground, 3 links moving freely. How many degrees of freedom does this thing have? 1, right? And I can pass this around. Don't hit your neighbor. It's heavy. And we can go ahead and look at the math. So number of degrees of freedom, you claim this is 1, will be number of bodies, 3 times 3 degrees of freedom per body minus how many constraints? Can you quickly count them? How many constraints? How many joints? 4 joints. And how many constraints per joint? In the planar case, 2 times 2 equals 1. Okay? Let's double check. 3D. NQ equals. We still have 3 bodies that can move. It's a 4-bar linkage, but I basically excluded that 1 body that is bolted to the ground. 3 times 6 minus how many constraints in the 3D case? So it's still 4 joints. How many constraints per joint? 5. So how many degrees of freedom does this give us? What? What's going on? Can you verify that this has 1 degree of freedom? Yep, he's verifying. No, that you did exactly what you were supposed to do. Verify that this has 1 degree of freedom. What's going on?
Some constraints are doubled. For example, if you twist one thing, then on this path and on this path both will block the rotation of the object on there.
You're going in the right direction, but I think your answer has a sign error. What did you want to say?
I wanted to say that the difference is that this is a closed kinematic loop, so you can't.
No, actually it has nothing to do with the closed kinematic loop.
We should close the ground somewhere.
Well, I did, right? So I said this was bolted to the ground. This is why I only counted 3 out of the 4 links. Right? It's called a 4-bar linkage, but I only counted 3 because I said that one's not going to move. Right? So if you basically hold it freely, you can do 7 degrees of freedom because you rotate and translate. Right now it's moving through the classroom, but I'm talking about this 1 degree of freedom. But what's going on here?
I think it's both joints on the inverted, they count as 1 maybe or something like that.
I think the 2 of you are going in the right direction, right? What happens here is that constraints are not independent. And the reason why that is because this thing was very carefully manufactured such that all joints align. They all point in the same direction. That leads to the fact that overall these joints are not independent. And I can show you a counterexample, which was less carefully manufactured. Actually, if you ever do this with a real machine shop, this is much easier than that, right? So I had to explain them about 3 times. You want me to do what? Every hole should have a different direction. So this is the same 4-bar linkage, but with, well, with bad holes. And what you will see is that you cannot even put it together. As much as you try, there's always going to be 2 degrees of freedom that don't fit. I either have basically the Z position not aligned. I could go ahead and align the direction of this axis, but then it's basically an X and Y. I could get here. If I move around, you give it a try. This is more fun to play with than the other one. Also heavy, don't hit your neighbor. In a real 4-bar linkage, in an arbitrary real 4-bar linkage, where these axes are not perfectly aligned, we cannot even assemble the whole thing, which is indicated by the -2. The -2 actually means I have to break 2 constraints in order to be able to assemble it, which I basically did when I took out that 1 screw. -1 would still mean cannot be assembled. 0 would mean what? Doesn't move, right? You can assemble it, but it doesn't move. And then 1 is the other thing that is being passed around. So here we have to be a little bit independent. Constraints, in this case, are not independent. And that is why the 3D case cannot be assembled in a general way. So this equation is true. But in the exception that we built, where the joints are aligned, we get 1 degree of freedom. So be careful here. This is not always true. And we get to this a little bit later, when how to then formally assess these numbers. So joints do 2 things. They enable and they restrict motion. And that's mostly a point of view, right? If I have a cast and a stiff leg, and the cast comes off, then my knee joint can act again, and I get a joint that now enables motion that I didn't have before. Right? If I look at the door, if I take out the pin obviously was restricting the motion of the door, because afterwards I can pack the door and take it with me. I'm making that explicit distinction because each of these comes with its own mathematical formulation. To highlight that a joint enables motion, we will write something that I will call an explicit constraint. And to highlight that a joint restricts motion, I would write it as an implicit constraint. An explicit constraint will be formulated as some vector x, which is at this point very loosely defined, but is basically the motion of the bodies is an explicit function that we call fc, the constraint function fc, of the generalized coordinates q that describe the motion in the individual motion primitives. So these are the generalized coordinates. That is q, and x describes the motion of my bodies. And here we have nb times 6, or in the 3D case, nb times 3 variables. Right? And without going into the specific, this vector x for each 3D body should somehow encode 3 translations and 3 rotations. For each 2D body should encode 2 translations and 1 rotation. And basically what this function fc does, fc, sorry, that looks a lot like a u. fc, constraint, not unconstrained, constraint. It maps somehow these nq degrees of freedom that we have in our motion primitives onto the axis. And this is what I mean with an explicit constraint. I know what the joints are doing, and I'm trying to figure out what are the bodies doing. The implicit constraints look different. There, I take a function gc over this variable x. So gc is my implicit function. And then I ask for the result of this function to be equal to 0. So this is my constraint equation. And the number of zeros, or the number of elements in the 0 vector, is equal to nc, the number of constraints. nc constraints, nq motion primitives. This, I think, is easy to understand. That one, a little bit harder to wrap your head around it. But basically what it does is for every 0 that is here, I have an additional equation that needs to be fulfilled. And each of these equations limits what my x can be. Here it's explicit. X can only be what is described through the q's. Here x at the beginning can be anything, but each of these equations takes away 1 degree of freedom. Question? Yes?
NB is the number of lines, right?
Yes.
Is there a reason why there's a vector sign on top of it?
No.
And second question.
Yes.
So a joint must exactly constrain all the motion in that degree of freedom, or can it work as an extra stiffness, like a spring or?
Okay. Sorry. Let me interpret your question as, for us, joints are rigid. So a spring, which would still allow motion, is not really constraining anything for me, right? So if I have, that door, well, that one doesn't, but some doors have a spring in them that pushes them close, but you still have that degree of freedom. So I would still consider this to be a motion primitive. Did that answer your question?
Yeah.
Okay.
But it would add an extra implicit constraint, like not the constraint but the equation to our system, or?
No. It will influence the equations of motion because it generates torques and forces, and that changes accelerations, but it doesn't prevent accelerations. And here we're talking really about things that prevent accelerations, that prevent motion. I want to give you an example of these two, and it's actually a very, very simple example of the door that we have in the back of our classroom. And I want to go ahead and add a joint. And that joint will have a single motion primitive, a rotational joint, so it will have a single angle Q. And that joint is located at the point RBP. in body coordinates given as minus px 0. So what do I mean with this? Here's my body, and to describe the motion of the body, I add a coordinate system and I add a point. Coordinate system B, point B. And then within, that's a bad drawing, but within this body, I have a body fixed vector, right? Body, point B is body fixed, and then the location of the joint on the body is body fixed. So I have a vector RBP that connects the location of my body given B to this point P on the body. And that joint now connects to another body, in this case to ground. So here's ground. And on ground, that point P has also a position, which is here given in I coordinates as x0, y0. My body is B, and it has a position and an orientation in 2D, so there's a planar example. And I describe that with a vector x, which contains the coordinates of this point B. X and y would be the coordinates of this point B in inertial coordinates, I should say that. We'll write this down in a second. And it has an angle gamma, which describes the orientation of this body. So this would be, in this case, our vector x, right? 3 parameters that describe the position and orientation of our body. And to link this with what we had done before, I would say the position of point B, or the relative position of point B, is given through the coordinates x and y. And the orientation AIB is given through a transformation matrix with the cosine and sine terms of this angle gamma. So 3 variables to describe our body B. And then I could also go ahead and introduce here a joint angle Q. How do the explicit constraints look like? How can I compute x from Q? Who can help me? Kind of, yeah. I mean, this is, we haven't really done an algorithm for this yet. That's still to come. But I want to know the x coordinate of this point based on the value of Q. How do I do this?
X of B, correct?
Hmm?
X of B or X of I?
X of B in I coordinates. Right? This is my definition of x. The first coordinate of the vector RIB in I coordinates. What is that? So I start at I, then I go x0 to the right, which brings me to point P. And then I go a little bit more, which is dependent on this distance between P and B, and also on the angle Q here. So that Px times cosine Q. And this is the format that I want for an explicit constraint equation, right? If I know Q, I know my parameters, right? My geometrical parameters. If I know Q, I can compute X. What is Y? So I'll write here P of X because we don't have a P of Py. And so there's just one distance. What is gamma? Simply Q. The biggest mistake you can make here is that you write a gamma here. Right? That would not be allowed. X, everything in green, has to be an explicit function of everything in blue, which in this case there's just one blue variable, right? And then to formulate my function fc, vector valued function, first element would be x0 plus px cosine q, second element would be y0 plus px sine of q, and angle gamma would be equal to q, and that is my fc of q. And here explicitly written as a vector, but q is only a scalar. So that would be the explicit constraint formulation. How about the implicit constraints? That's this distance. This here, that's px. Implicit constraints, right? We now have to think about this the other way. Where's the motion restricted? And one way to do this is to say that the position of our hinge from the perspective of ground, right? And from the perspective of ground, the position of the hinge was given as RIP in I coordinates, that this should be equal to the position of the hinge from the view of the door. And from the view of the door, I would have to say that is RIB in I coordinates plus the contribution of this vector RBP, which is given in body fixed coordinates. This is why I pre-multiply it with this matrix A. And then I set the difference between these two equal to a vector of zeros. So what I'm saying here is locate the hinge at the door frame, locate the hinge at the door, and if they're at the same location, the difference is 0. And if they're at the same location, I can put the pin through the joint. And that is my constraint. And now we can go ahead and write this in coordinates. So this would be x0 and y0 minus. This is x and y, the position of the joint. The position of the body. Then we have here a minus sign, if I get rid of the parenthesis, AIB times, we had this local coordinate vector px and 0. And now we see that I have two constraints. Right? It's a two-dimensional constraint equation. I do have two constraints. And I can now go ahead and write my function gc as being x naught minus x minus px times cosine of gamma. And in the y direction, my constraint is y naught minus y minus p of x times sorry, I missed the minus sign here. Just confused, but this is defined as minus px the way I drew the coordinate system. So there must be a plus here, a plus here. Doesn't really change things. Here's a minus sign as well. Sine of gamma. Equal to 0. And those two things mean exactly the same. They describe exactly the same constraint, simply in two different forms. In an implicit form, where I have this implicit equation, gc of x is 0, an implicit equation. And in an explicit form, where fc of q gives me my position x. Which of these is better? Why? Fewer number of equations. In general, fc is harder to get than gc, but it's easier to work with, right? Explicit equations are always easier to work with, and you basically break everything down to a fewer number of variables, because q is only the number of motion primitives, and x would include everything that your body could do without the joint. These equations are easier to derive, and they're harder to work with because they're implicit. Turns out we will need both. If you want to know how your leg muscles are moving your knee, your leg muscles are basically working in this Q space, and it makes sense to think about this set of equations. If you want to know whether your ACL survives a skiing accident, right, the ACL lives in this, well, it doesn't have a name, but in that space that has to be 0, right, in that constraint space. And in order to figure out what forces we get in that constraint space, we have to work with the implicit constraint equations. Quick questions? Yes?
Can we also implicitly restrict the motion by setting the velocity is equal to 0?
We'll get there. Yeah. But at this point, I first want to look at things on position level. Yeah. So these are holonomic constraints. Other questions? I have a question for you. What is the relationship between FC and GC? So if GC of x is equal to 0, and x is given as fc of q, what do I get when I take gc of fc of q? What is that? GC of fc of q has to be 0. This equation only allows x that are consistent with my constraint. And if I put an x that is consistent with my constraint into the implicit constraint equation, the constraint is going to be fulfilled, and it will give me 0. So that is the relationship between these two. And if you want to, it's easy to verify this with these equations, but we're not going to do this. Instead, I want to add an important disclaimer that what I've wrote down here only holds, of course, if GC and FC describe the same constraint. Not important now, because there's just one constraint on the page. But a little bit down the road, we will have multiple constraints. Some of them will be explicit, some of them will be implicit. And then, of course, this relationship only holds when I talk about the same constraint. Next step, velocities. Right, and this is in your templates, just written down cleanly, implicit, explicit constraints, and then sort of this note that we haven't really discussed what x means, but we get a feeling that it somehow encodes the motion of bodies through Euler angles, through position vectors. But I want to keep it very general, because down the road we will also use it to label other things x. If you think about a robot, maybe you're just interested in the position of its end effector, and then you just assign a position variable x to that position without really caring what the bodies are doing. So we can use this in a very general way. If I have an explicit constraint, x equals fc of q, and I want to know what is the velocity of this body. So what is x dot? I would have to compute the time derivative of fc of q against time. But here we have nested functions, and I can apply the chain rule, and I say that is equal to partial j partial q times dq dt, and dq dt is equal, or we will write as the angular, the generalized velocity q dot. That is the time derivative of q. And before that, I have this partial derivative partial jf partial q, and this would be my constraint Jacobian jf. So a Jacobian sometimes this get other names. In some books, this would be called S, my constraint Jacobian. And with this constraint Jacobian, I can write a linear relationship between the velocities of my body and the velocities in the motion primitives. So x dot is simply jf times q dot, where jf is the partial derivative of my constraint function against my generalized coordinates q, which is a matrix. What are the dimensions of jf? How many rows? How many columns? Partial derivatives. So f is a function. How many elements are in this vector f? How many rows? Well, as many as we have x, right? So this has to be a matrix that has nx rows. How many elements are in this vector Q? Well, nq. So this is an nx times nq matrix.
Question, how do I know how many equations I need for these explicit and implicit constraints? Is there like a rule of thumb, or
It's a good question. I mean, this is what I was trying to highlight here, right? You can count your motion primitives, right? For every joint, you know how many degrees of freedom it has. You can count the number of bodies, and then you would get basically the numbers that we see here. Can I come back to your question in a second? Because often it's trivial, right? If you have a robot and it has a rotational joint, every rotational joint needs a Q. If the same robot, right, every body has 6 degrees of freedom, we're good, right? But there are situations where it gets a little bit more murky, and we'll get to this. I want to first do the example. So x equals, right, that was our explicit constraint. So I now need the constraint Jacobian. So x dot equals now a constraint Jacobian. So the partial derivative of this function against q, in this case that's not going to give us a matrix because q is one-dimensional. But what's the partial derivative of this matrix against q? So x naught against q is 0. Px cosine q against q is px sine of q. Here I get plus px cosine of q. And then q against q would give me 1. And we see this is a function of q, right? This jf is a function of q, and I should state that explicitly up here, and you should just make a note of that, right? That jf depends on q. It's not a constant matrix, but it is a variable matrix that depends on my configuration given by q. And then I have to multiply this with the vector of generalized velocities, in this case just the value q dot. I want to show you a quick example. Let's see how well this works. What I have here is the situation depicted on the lecture notes. And what I did was I computed x. So here's our fx, our function. And then here I computed jf, or wrote it down. Px sine q plus px cosine q 1. And then I simply visualized this here in this little drawing as the green line. So the green line is basically the vector in this matrix, or the vector that represents the column of this matrix JF. What is it telling me? It's a line, right? It's a direction. It's basically the direction in which the body can move. Right? At this point, if I'm sitting on a hinge here, this is the point B. Point B can only move in this direction. How fast depends on how I choose q dot, but I cannot change the direction. And this is what we see here mathematically, right? By changing q dot, I can change the velocity, or I can change the speed with which the door moves, which it rotates, but I cannot change the direction in which x will move. So the columns of JF describe the motion subspace. Of the system. So it gives me the directions of possible motion. And that follows directly from the map, right? Each column of this matrix JF gets multiplied with the velocity in the motion primitive. If I get to choose the velocities and the motion primitives, the resulting motion has to be a linear combination of the individual columns of this matrix. And in this case, right, the matrix is a 1 × 3 matrix, so I only have one direction in which I can move, which is shown here by this green arrow. By the way, the green arrow, this will become important in a second, the green arrow is 3-dimensional because I have a hidden gamma direction, right? I can move in this direction, but at the same time I have to rotate my body. I cannot independently move the point of the body without rotating it, so I have just one direction of motion which combines motion in x, motion in y, and rotation. And this is here, let me rotate this, right? Then you see this is really a 3D vector. And in the view that we have, it of course corresponds to moving along this arc, right? That point, because here's my joint, can only move in a circle. That's the meaning of JF, the directions in which our system can move. What about implicit constraints? And for implicit constraints, I would now start with the implicit constraint equation. 0 equals GC of x. And I do the same thing, right? I take my derivative, the derivative of a 0 matrix, well, is simply a 0 matrix. It's equal to, and now I do the same trick, right? I need the total derivative of GC of x against time. But what I will do is I will take the partial derivative of GC against x and multiply that with the derivative of x against time, which we will simply call x dot. And again, I get one of these Jacobians. This one I call JG, and I will actually call this the transpose of JG. So what I get here is that JG transposed, which now can be a function of G, times x dot has to be equal to 0. And JG transposed is defined as partial JC, partial x. What are the dimensions of JG transposed? You can read my handwriting.
Yeah, what is the letter under DG?
DG here?
Yeah, it was there.
Oh, that should be a T. It's not a matter of handwriting, but of correctness. Sorry. If I said I do this on purpose to check if you're paying attention, would you believe me? No. Oh, come on. Dimensions of this guy. Well, it maps from X to our space of zeros. So it has a row for every constraint and a column for every x. And you still can't read my handwriting? No. And I should make a note, since I had this on the other, this is sometimes called T. Or T transpose, which I will try to avoid here. In our example, GC of x equals 0, so GC dot of x is now, I need the partial derivative of this function against the elements of x, and I will get a 2 by 3 matrix. I get a -1 here, a 0 here. If I take derivative against x, I get a -1 here, nothing down here. I get 0, -1 if I take a derivative against y. And then I have to take derivative against gamma, which will give me a minus px sine of gamma and a plus px cosine of gamma. And then that matrix gets multiplied with our velocities in the x space. So x dot, y dot, gamma dot. And the result of this should be equal to a vector with 2 zeros. How do I read this? I suggest you read this as a bunch of dot products, right? There's a matrix product, but matrix product is row times column. So that row times that column equals 0. That row times that column equals 0. In other words, the dot product of this row with that column is 0, or that row on that column are perpendicular to each other. That row and that column are perpendicular to each other. So JF gave us the directions in which we were able to move, right? The directions in which x dot, y dot, and gamma dot could point. Because here we computed x dot, y dot, gamma dot as this direction times some velocity in the motion primitive, times some generalized velocity. Here we're doing exactly the opposite, right? I'm saying you cannot move in this direction. The direction in which you want to move has to be orthogonal to the direction given in this row, and it has to be orthogonal to the direction given in this row, right? So the way you should read this constraint equation is as a bunch of dot products where the velocities that we can get have to be orthogonal to the rows of JG transposed, or if I look at JG, right, orthogonal to the columns of JG. So the columns of JG describe basically the directions in which I cannot move. So JG describes the constrained subspace. J, G. Jacobian, this guy here. That is JG. Right? That is the Jacobian now of my function G. JG describes the constrained subspace. Of the system. So those are the directions in which I cannot go, the directions of blocked motion. And I added the directions of blocked motion to my little diagram here. So those are the red arrows. Those are the columns of JG. Column of JF, columns of JG. Maybe not what you expected, right? Because I just said the direction in which I can move, which is green, has to be orthogonal to red, right? And so we would have maybe expected an arrow pointing this way, which basically would tell me, oh, right, that point, it can go this way, but it cannot go towards the center because that's where the constraint acts. This looks different, right? But two things. First of all, this is 3D because this includes rotations. And if I look at this from 3D and also take into account the rotations, we indeed see that the directions in which we can move are orthogonal to the directions in which we cannot move, right? So those two arrows, they generate a plane that sits somewhere in here. If I rotate this, you hopefully can kind of see the plane. And the green arrow sits orthogonal to that plane. So kind of describing the constraint in two different ways. Green arrow, this is what the body can do. Red arrows, this is what the body cannot do. And in particular, the vector that we would expect, we see that that sits within this plane, right? We're not talking about individual directions, but spaces. And I could span that space many different ways. An easy way to get a different constraint formulation is by simply multiply a 2x2 matrix to this function, right? And if I do this on the left and on the right-hand side, I would still get a 0. So the directions of this constraint function GC don't really matter. I could completely reorient them. So I'm here just looking at the space. So what that means for me is I'm interested in this plane. And you can kind of see that that plane nicely intersects with this point, which sort of corresponds to this idea. If I don't allow any rotation, right, then I cannot go in the direction that we see here, right? So this is why in this view, I would expect an arrow pointing from here to here. And that arrow exists as part of the plane of the subspace spanned by the two red arrows. Questions? Yes?
These vectors are the rows or columns of JG?
Say that again?
These are the rows of JG.
These are the columns of JG, right? Here we have JG transposed. So that's why we look at rows. But then JG, of course, is transposed. So these are the columns of JG. These are the columns of JF. Relationship between the two. 0, we said, is JG times X dot. Pardon me, JG transpose times X dot. X dot is JF times Q dot. So JG transposed times JF is equal to what? JG times JF. Well, if I insert this, right, if I compute JG transpose times JF and multiply it with some arbitrary Q, I would always get 0. So JG transpose times JF should be a matrix of zeros. In this case, a matrix of dimension NC cross NQ. And what I'm writing here is basically that every column of JG is orthogonal to every column of JF. This is what I just showed you in the animation. The directions in which I can move, JF, and the directions in which I cannot move, JG, of course, they should be orthogonal to each other. I can now circle back to the problem that was phrased originally, because we now talked about the directions in which I can move, which are given, I said, by the columns of JF, and the directions in which I cannot move, which are given by the columns of JG. These are spaces, and the dimension of the resulting space is not always equal to the number of vectors spanning the space. Right? If the vectors spanning the space are dependent, I would get a lower dimensional space. Meaning, if we're interested in how much degrees of freedom do we really have, we have to go ahead and look at the rank of these matrices. The rank of JF that is the number of available degrees of freedom. So the number of independent columns that is the number of available degrees of freedom. The rank of JG of X is the number of independent constraints. So this guy, where's the other guy? The murder weapon? This I want back. Everyone has one of these, but that is the rare one. Right, going back to this puzzle. Someone tighten the screws here. Going back to this puzzle, if I would generate this matrix JG, it would have 5 rows for every individual joint. 5, 5, 5, 5. So I would get a matrix that has 20 rows. But if I would compute the rank of this matrix, it would only have a rank of 17. Because somehow these constraints are linearly dependent, which is a function of the fact that they're all pointing in the same direction and that they're all coplanar to each other. Right? They're all in the same plane. They're all pointing exactly the same direction, carefully manufactured this way. And because of this, I will get dependency in these constraints. Mathematically, they will show up as a loss of rank in this Jacobian. So the Jacobian of this guy will only have a rank of 17, even though there is a total of 20 constraints. And then in this guy, where we don't have this careful alignment of constraints, we will not see these dependencies. Right here, all 20 constraint equations are independent, and you can bend it as you want without ever being able to assemble it. Same holds for potentially for JF, that we can lose rank. Now, since these two matrices are function of Q and of X respectively, the rank can change depending on the configuration, right? So they can lose rank in certain configurations of, well, Q and or wrong color, Q or X. And then they would produce something that's called a kinematic singularity. And just on Tuesday, we talked about such a kinematic singularity, which was the gimbal lock. If you remember, what we did was we identified this guy here. Actually, I should write it without the inverse, right? If I get rid of the inverse, then this would come to the other side, and I will get that my omega IC, the angular velocity of my body, so this is basically my x, right? My motion in Cartesian space, x equals AIC times b, this matrix, times here my three motion primitives, which are the three Cardan angular velocities alpha dot, beta dot, gamma dot. Typically have, this is a 3 by 3 matrix, rank 3 independent degrees of freedom. But in the situation of gimbal lock, we saw that this matrix here loses rank, right? We can tell because the inverse doesn't exist anymore, right? We divide by 0. So for cosine beta, for beta equals 90 degrees, cosine beta becomes 0. So for beta equals 90 degrees, this guy is losing rank. And this is what I showed you in the animation, where the first and the third axis of rotation are aligned. So I get one rotation here, the same rotation here, right? So those would be the columns, right? These axes of rotation, those are the columns or correspond to the columns of my JF. And if two of them are the same, like pointing in different directions, but they're collinear, right? The same apart from the sign. I only have a rank of 2. I have 2 independent directions in which I can move. I get into a kinematic singularity. And that becomes problematic if I want to invert things, right? If I want to compute those derivatives based on the velocity here. So not something that we haven't seen. Quick questions? Let's do one example. And what I have here is a quadratic roller coaster where I have a particle somewhere here, which is described in my x world as a point with coordinates x and y. And my motion primitive is the motion along or in the direction of the x-axis, and my constraint is that this particle is basically moving on a parabola. So think of this as the rails of a roller coaster, the track of a roller coaster, and your point mass is moving this way, and from the outside I'm only measuring its x position, but of course due to the roller coaster design it also has to move in the y direction. So in this case, my x vector describing the motion of my body, or in this case a point mass, is the x and y coordinate of this point, which is given through an explicit constraint formulation as a function of a scalar value q. And my explicit constraint equation would be x is equal to q and y is equal to q squared. Implicit constraint equation, GC of x, I can write as saying, for example, that x squared minus y is equal to 0. Right? That would be the same constraint in implicit form, x squared minus y is equal to 0. X dot is JF times Q dot is the partial derivative of this against Q, so I get 1 and 2Q times Q dot. And then for the implicit constraint, I have that 0 is equal to JG transposed times x dot, where jg transposed is the partial derivative, so we would get 2x and a 1, sorry, minus 1, of course, times x dot, which are the velocities in x and y direction. And now I can try to visualize this. So this guy always points 1 in the x direction and 2q in the y direction. And if you know a parabola, right, its slope is always 2x. So what I get here are arrows pointing nicely along the slope. Those are the directions of motion. So this is visualizing these directions as a function of q. The directions in which I cannot move are orthogonal, right? 2x minus 1, so at position x equals 0, this points straight down with a minus 1. And then if I move to the right, I basically get still 1 in the negative y direction, but I would get, that was not very orthogonal here, y in the minus 1 in the y direction, and then 2x in the x direction. So here on the negative x side, I will get arrows pointing to the left. So just visualizing this idea of directions in which I can move, columns of JF, directions in which I cannot move, columns of JG, or here the rows of JG transposed. Has the? Magnitude of JG transpose? Not really, because it evaluates to 0, right? If JG x equals 0, right, I could multiply any matrix B or whatever you want to call, and you're going to get B times 0 on the other side. So you can scale it, you can invert it, you can flip the axes or transform the directions. It doesn't matter. Of course, if you evaluate things later, right, and you will associate forces with these directions, then you kind of want to know what are the directions of the 0 that we talk here about. So at some point, this will become more important, but for now, it doesn't.
Does the magnitude of JF has a meaning?
JF, yes, because JF gets scaled with Q, right? So if JF is twice as large, then the same Q dot will give you twice as large of a X dot. Yeah. Okay, I think we should end here. Thanks for the questions. Have a good weekend. Don't forget the homework. I see you on Tuesday talking about accelerations.